back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 110, Balanced Binary Tree. Given the root of a binary tree, determine whether the tree is height balanced. That means for every node in the tree, the heights of its left and right subtrees differ by no more than 1. This single node tree is balanced. This single node tree is balanced. Its height is 1. Its height is also 1. The tree at root node 20 also balanced because the height of its left and right subtree differ by no more than 1. Its height is 2. This single node tree of course is balanced and its height is 1. The tree at root also balanced because the height of its left and right subtree differ by no more than 1. By the way, its height is 3. How about this tree? A single node tree is always balanced. The height of this tree is 1 and 1. The tree at root node 3 also balanced because heights of its left and right subtree differ by no more than 1. Its height is 2. This single node tree is balanced and its height is 1. This tree at root node 2 also balanced because the heights of its left 2 and right 1 differ by no more than 1. Its height is 3. This single node tree is balanced. Its height is 1. The tree with root node 1 is not balanced because the height of its left and right differ by 2. Here's the idea. We will use a bottom-up recursive approach. We write a helper function that runs at every node and does two things. Returns -1 if the subtree rooted at that node is not balanced. Otherwise, it returns the height of that subtree as we see on the left. Okay, let's translate this idea to Python. First, define the recursive helper function check node to be called at every node. This function will return -1 if the current tree is unbalanced or its actual height if balanced. If current node is none, means no tree, no height, we return 0. It's our recursive base case as we can see all 0 on the left. Otherwise, if it's a real node, we recursively check the left subtree, then recursively check the right subtree, and save their result into variables left and right. If either subtree is unbalanced, meaning it returns -1, or the difference in their height is more than 1, then the current subtree is unbalanced and we return -1. Otherwise, we return the height of the current subtree. So again, helper function check node return -1 if that subtree is unbalanced or its actual height is balanced. If the whole tree is balanced, result at check at the root won't be -1, so we return true. Now let's take a look at the lab example step by step. Is the tree with root node value 3 balanced? It will call the check function to find its height or return -1 if the tree is unbalanced. F of 3 will return 1 plus max of its left f of 9 and right f of 20. F of 9 return 1 plus max of f of none and f of none, its left and right subtrees. If not, node return 0, so f none is 0, so the whole evaluation return 1. Similarly, on the right, f of 20 return 1 plus max of f of 15 and f of 7. Just like f9, the result is 1. f15 and f7 result also 1. The height difference between f15 and f7 is 0, so we return the total evaluation which is 2. the height difference between the left and the right is no more than 1. So we continue processing with the total evaluation. Let's copy everything down to one line. So the result of f of 3 is 3, different than -1. So this evaluation return true. This tree is balanced. How about this tree? The only difference here is F7 will return 1 plus max up 0 and 1. Right, 1 here. This whole evaluation return 3. And the height of the left and right subtree differed more than 1. So we return -1. So F3, instead of returning this, it return -1. -1 is not different than -1. So the whole evaluation return false. So this tree is not balanced. Alright, time to smash the submit button. Moment of truth. Boom, accepted. This solution is both elegant and efficient. Time complexity big O of n because we visit each node exactly once. Space complexity also O of h, where h is the height of the tree due to the recursion stack. And that's it. This is a clean recursive pattern that shows up in many binary tree problems. Check something at the children, bubble up a signal if something goes wrong, and return useful data if not. If you found this helpful, be sure to subscribe to the channel for more Leetcode walkthroughs like this one. I'm Alan and this was Leetcode Simplified.